Okay, so before the midterm break, we were delving into yes.
From the midterm part. So why don't we take the resistance across the capacitor terminals to total resistance of the capacitor terminals?
Okay, so you mean in general or in a particular example? Okay, so when you say, so let's take an example and then see. So this is what we were doing. Okay, so I'll start from there. So let's take his question. Can you repeat your question once more?
So why did we take the total resistance of the capacitor terminals to
Okay. So yeah. So you are talking about this half, right? Okay. So why is it not going up? So let's redraw that part, right? So, I mean, if I sketch the small signal model of this, so what should I get here? Assuming, let's say, C1 and C2 are large enough to start off, right? So I'll know that this voltage is whatever. I mean, by the way, what will that voltage be? What will be incrementally? What will that voltage be? So in order to figure out incrementally what will that voltage be, I can sketch this, sketch the incremental model of this circuit. And the incremental model of this network will be as follows. So this is VG, this is R1, and this is incrementally grounded. This is R2, incrementally grounded. RD, let's keep the capacitor to start off. This is GMVG. Okay, so let's do the part on the left, then we'll do the part on the right. In the part on the left, if we have to, I mean, if capacitor has to be sufficiently large, certain condition needs to be satisfied, right? Ideally, I want C1 and C2 to be large enough so that they are shorted at the signal frequencies. Now, if they are to be satisfied, if that assertion has to be satisfied, then what do I need to? What am I essentially saying? What I'm essentially saying is that the voltage drop across C1 has to be much lesser than the drop that that I'm having anywhere in the loop. Right? Yeah. So what is a short? What does a short essentially mean? I mean, so let's assume I have any bunch of impedances. Let's say Z1, Z2, Z3, Z4. Right. So you have you have a bunch of impedances, and you say that, for example, I say that I have a I figured out what is a voltage drop across VZ2, and I would want this voltage drop across VZ2 to be much lesser than something, right? Now, what is that something will determine that condition, correct? So in this case, in this particular case, what we have is we don't have this network, we have this following network. RS, instead of Z1, you have 1 over j omega C1. And on the right-hand side of that, you see a parallel combination of R1 and R2, right? Looking here, it's a parallel combination of R1 and R2 because, I mean, I can sketch this. This is annoying. Why this is not going on? Stop sharing. Okay, great. So, so in this case, you have R1 parallel R2. And when I said that this capacitor has to be short circuited, essentially what I'm saying is VC1 or the voltage drop across C1 has to be much lesser than the drop anywhere in the loop. Right? So in terms of impedances, it translates to the impedance of the capacitor has to be much lesser than the impedance that it sees across it. And the impedance that it sees is RS plus R1 parallel R2. So your condition becomes 1 by mod of 1 by G omega C1, that is, this should be much less than RS plus R1 parallel R2. And then you obviously get the relation that C1 times RS plus R1 parallel R2 has to be much lesser than 1 over omega. Okay. So now, before I move to the right-hand side part of the network, the output side. Ideally, yes, but let's assume the capacitor is shorted. In that case, in the presence of RS, VG, there will be a voltage division, right? So, let's assume there is RS. You cannot do away with RS in any practical circuit. There will be a resistance associated with any source, right? So there is an RS. So in that case, what is the best you can do? You can then say that first let's attack that if what condition needs to be satisfied in order to make sure that C1 acts as a short. Now, if that is satisfied, then what voltage do I get across VG? VG will be not approximately, VG will be equal to R1 parallel R2 by RS plus R1 parallel R2 times VI, right? Now, note that RS is not in your control because it's probably coming from some specifications, a previous stage, but R1 parallel R2 is in your control. So as a designer, if I want this to be almost equal to VI, I can choose R1 parallel R2 in certain way, right? I can choose that if I want this, then choose R1 parallel R2 to be much greater than RS. If you choose this, then VG becomes almost equal to VI. Right? So, so essentially that's what it boils down to. Okay.
So R1 and R2 resistance VI, so you see the resistance we can't cover is RS, and RL is our load. What is RD?
I'll come to RD. I'll come to RD. So we are still at the input side, right, in the discussion. I'll come to RD. So, is this part clear till now? What I have done. So mathematically, this is simple algebra, right? But I want to drill in the thought process behind it. So what is the first thing? The first thing is, I mean, we cannot do away with the capacitor C1 because ultimately that C1 acts, and we wanted a floating battery, which we cannot have. So we replaced it with a capacitor. The large enough capacitor acts as a battery. Now, what is large enough? What is the metric of large enough? The metric of large enough is essentially the fact that the voltage drop across it, right? Incremental voltage drop across it should be much smaller than the voltage drop anywhere in that particular loop in which the capacitor is placed. So what is that loop in this case? That loop is this. If you satisfy this, if you satisfy that the voltage drop across the capacitor has to be much lesser than anywhere in the loop, that is the sum total of voltage drops across RS and R1 parallel R2, then you get certain condition on C1. Now, that is satisfied. But note that ideally, I would also want the entire voltage VI to appear across VG. So if the condition of C is satisfied, the next thing that as a designer we'll have to choose is the things that are in our control, that is R1 and R2. Can I choose certain values of R1 and R2 so as to ensure that VG is equal to VI or almost equal to VI, right? And obviously, I mean, it's a voltage divider. It's a voltage division between RS and another resistance, which is R1 parallel R2. So if I ensure that R1 parallel R2 is much greater than RS, then obviously there I'll not have any voltage division, or I'll have minimal voltage division. So I'll get almost whatever I have applied at the input terminal VI across VG. right? That essentially is the thought process. And the other way of okay, so and if I take a step back and I go back to the if I take a step back and I go back to the way of figuring out the capacitance, obviously this is an exact method of figuring out what is the value of capacitance. But generally, what we as circuit designers we try another abstraction, and the abstraction is that of a time constant, right? So what is the time constant of this network? If I tell you, RS, what is the time constant of this network? P1 times RS plus R1 parallel R2. And just to ensure we all are in the same page, can I define time constant of a second order network? We can only define time constants for first order circuits, right? Because ultimately the concept of time constant comes because you have in case of a first order network, I mean, if you simply have an RC and you, let's say you charged it with some voltage VC naught, and you write out the equations, right? You write out the current equations, then your current equation, what will that be? It will have, so let's assume this is VC. So C dVC dt will be the current, right? Which will be equal to in this particular network plus minus. So when I say C dVC dt, which direction of current am I implying? Right. So current from top to bottom in the capacitor. No, I mean, okay, forget about discharge. It will discharge too. But when I say that your current through the capacitor is C dVC dt, what? No. Okay, we'll get to that. What I'm implying is, okay, forget about this network. Let's say I have DC, and what is the current I in terms of? It's not VC by R.
Minus C times dVC by dt.
Going which direction? In the direction that I have shown, what will be the capacitor current relation? Right, C dVC dt. Right? So it will be minus or plus? Yeah. Right. So expression is fine, right? Whether it will, depending upon if VC increases or decreases, this entire thing will become plus or minus. Right? So in this particular, now if I turn my attention here, right? If I turn my attention here, what do I get? This. If I solve a KCL at this node, right? So C dVC dt is the current that I'm flowing through the capacitor, and total current into that node has to be 0. So essentially this plus VC by R has to be 0, right? And then you solve, right? You get an exponential. When you solve this, you get some exponential relation, and this phenomena obviously you see in many physical. When you do this half-life measurements and all, right, you always get you get this type of differential equations, and we know how to characterize them. We characterize them in the form of some time constant, right? So what is the time constant in this thing? I mean, this is simple. In this particular expression is simple. This will become VC some initial condition times e power minus T over RC, right? And if I sketch this out, so this is VC over T, sorry, VCT, 0, and this is what you are going to get. And this at T equal to RC, you go to your VCT becomes initial value divided by E. So let's assume this. So this is RC. This drop becomes VC naught over E. And this, note that this fraction of this drop is independent of from where you started. And that is why this concept of time constant becomes critical, because you can comment on how fast the network is based on your time constant. If RC is very high, then what will happen? This will keep on holding the voltage for long time. And if the RC is very small, it will discharge very fast. Now, if you want a capacitor to act as a battery, you would want RC to be high or low. You want it to be high. You want this to be so high that it never discharges. Right? You want the RC to be extremely large. So that is why we tend to often say that, note that it's not the value of the capacitor only that matters. It's the value of R times C, right? Because it's not only sufficient to have a large capacitor, you need to ensure that the capacitor keeps holding that voltage. And whether it will be holding it or not also depends upon whatever is a resistance associated with it. If you have a very small resistance associated with a large capacitor, the capacitor will discharge easily. In that case, you cannot say that it's a good battery or it's a good approximation of a battery. If you have to get a good approximation of a battery, you have to ensure that the RC time constant or the time constant associated with the capacitor has to be really large. Okay, so now, as you again, I mean, this is another thing to ensure that we are in the same page. In this network, if I give you any network, right? If I give you any arbitrary network, and I tell you that there is one capacitor associated with it, and inside this network, I have only our control sources, all sorts of control sources and resistors, no memory elements, that is no capacitors inside, no inductors inside. How would I figure out what is the RC time constant or the time constant of this network? Right. So all I have to do is to figure out, looking in here, what is the Thevenin impedance? And this Thevenin impedance will be real. It will not be imaginary, because I don't have any memory network. I don't have any capacitors or inductors inside, which means that I should be able to, by the way, if I have a bunch of voltage sources and current sources also, in order to figure out what is the time constant, what should I do? Right. So I need to figure out Thevenin equivalent, which Thevenin impedance, which means I need to short this out. I need to short all the voltage sources, open all the current sources, figure out what is the Thevenin impedance. And if I do this, I should be able to get an equivalent resistance, right? I should be able to reduce this to an equivalent resistance, which is RTH in parallel with the capacitor, which means I know what will be the time constant. Time constant will be RTH times C. Okay, so now when I have this time constant, then I know now that I am in the familiar territory. I need to ensure that this time constant is much greater than 1 over omega naught, right? So this is the condition that we ended up with. Where was it? Yes. So essentially, this is what we are after, and easy way to come up with this condition without doing too much of circuit analysis is to essentially to look at your network and see if you can reduce it to a bunch of first order networks, or at least one first order network. If you have this first order network, then obviously you can associate a time constant with the network. Once you can associate a time constant, and you are trying to figure out that whether the value of the time constant is such that I can use the capacitor as a battery, then all you have to do is to ensure that find out the time constant and set it to be much greater than the frequency of interest. Okay, so that essentially is the method. Okay, so now let's move to the output side of this network. So this was VG. I'm not sketching the input side because I'm assuming that the VG has been set. Yes. Yes.
to have a constant voltage. Earlier in our transient analysis.
Right.
But here, so we have a variable voltage.
Okay, okay. So let me understand your question first. Is your question the fact that what happens if I have a control source inside? Fine.
So the time constant is corrected because the time constant is fully amplified constant voltage.
You mean when you have a step input,
Yes.
right? Okay, so that's what. Yes. Does your time constant? This is actually very fundamental question. Does your time constant depend on the type of source that you have applied, or it's the property of the network? It's a property of the network, right? From that, now the question is, from that property of the network, can I infer certain other things about the network? Right? So if you agree with the fact that it's a property of the network, then what type of input I have applied shouldn't matter. Right? So I extract that information that, okay, if RC, if the time constant is this, if the time, I mean, very crudely speaking, if the time constant is very high, I can say that the capacitor inside is holding on to its charge. And if the time constant is low, the capacitor is discharging its charge easily. So that is with respect to what you are saying is right. That is with respect to applying a step input, right? Or if you are initially charging the capacitor and trying to see how fast it's discharging. Perfect, right? Now, as it turns out, we have what we have seen in the classes before the midterm. This time constant of a first order network is also associated with the corner frequencies of your Bode plots, right? So there is a direct correlation between the time constant which you are deriving from step input responses to how a sinusoidal steady state response will behave. How will the circuit behave under sinusoidal steady state response? So the association of time constant is not only limited to step input, it's also limited to, it's also a function, it also has an implication on how the circuit will behave when you apply the sinusoidal input, right? So because in this case, in this particular case, right? Let's do this, the new case, right? So in this particular case, if I associate my time constant, right? So if I sketch the incremental model, what do I get? I get GMVG, you had VG here, RD, RL, C2, and I need to figure out what the constant on the capacitor C2 is. And going by the argument that I just laid out, if you buy into that argument of time constant, right? So what will the time constant associated with C2 be? So let me sketch the circuit a bit more accurately. So this is VI, and you had RS and all those things, and we assume that we have sized the input side such that VG is almost equal to VI. So now, in order to figure out the time constant of the network, what should I do? First thing, what should I do? Again, time constant is a property of the network. It doesn't depend on the input.
Apply a voltage to between for the terminals of you can find the
Even before that, you have to desensitize the network.
we can share in this case G into G. Actually, an ideal current source in this case.
Correct.
So and basically you need to find the right resistance.
Right.
So we can just simply open this.
Right. Perfect. So if I take even a step backwards, why would you like to open this?
Shorted.
Because VI will be shorted, right? So in order to figure out the time constant, you have to desensitize the inputs first. What is your input? Your VI is your input. You de-energize that. This goes to 0. If this goes to 0, this goes to 0. It's a current source. Going to 0 means this doesn't exist. Right? If it doesn't exist, then all you are left with is this network, right?
Focus to the right path.
Correct.
Trying to get a same as
Right.
kind of expression.
Same with the kind of expression, looking into the time constant, right? Before the midsum, we were looking into this through the Bode plot, but we are trying to equate whether those two are identical. So now, what will be the time constant associated with the capacitor? C2 times RD plus RL. And this should be much, much greater than 1 over omega. Right? So time constant methods are extremely simple once you figure out how to figure out the time constant. But you need not know time constant in order to figure out this expression. You can also go by the brute force method. And what is the brute force method? That is the one that we had discussed before the midsem. And that is as follows. So what you will have to do is this is grounded. So this is GMVI. So what will be V naught? This C2 is essentially an impedance of value 1 by j omega naught C2. Assuming that VI is applied at omega naught, obviously. So what will be V naught? Help me out. So you can do it incrementally, right? I mean, incrementally as in you can divide the problem into multiple parts. You see that this current is GM times VI. This current comes at this node and it has two ways to go. It can go either this side and it can go that side. Correct? So there will be a current division. So what is the current that is going into that node? That current is minus.
So we're finding the tau, the tau we GVI as a normal current, which we just move.
While finding the tau, we have to desensitize the input. So the moment we desensitize the input, that current source went off. But you note that it need not necessarily be that the current source will go off always, right? Because I mean, there can be, it's dependent, right? Essentially, we are trying to figure out the Thevenin impedance. In some cases, when you are doing Thevenin impedance, the current source can go off, and sometimes it might not. Then you have to calculate. Okay, so in this case, the current that is reaching this node, right? The current that is reaching this node is minus GM times VI. Then it has two ways to go. It can go either to the right or to the top. How much will go to the right? No, in terms of the current, right? So let's say I have a current. Let's say I have a current I. It has two ways to go. Z1 and Z2. How much will go to Z2? How will I know? No, right? It will be Z1 by Z1 plus Z2 times I. Correct? So, I mean, quick sanity check is Z1 is 0, all the current will go through Z1, right? So Z2, current through Z2 will be 0, right? So in this case, how much current is going into the capacitor? It will simply be RD by. But I am interested in the voltage across R2 or RL in this case times RL, right? So this is V naught. Okay. So in this case, if the capacitor is supposed to act as a short, which essentially means that I want this term to be much lesser than this term, which means again you get the same, you come up with the same constraint, that is C2 should be much, or rather in this case 1 over omega naught C2 should be much less than RD plus RL, or which in terms of time constant will mean that C2 times RD plus RL much greater than 1 over omega. Okay, so I think I hope I have been able to convince you that you can come up with the same conclusion both by using the time constant method and the Bode plot method or sinusoidal steady state method, because they are related, right? But I mean, the thing that sometimes trips students off is exactly the question that you said, that I mean, hey, time constant we have learned because when you give step inputs. And this omega naught stuff when you comes about when we were giving sinusoidal inputs, right? So what is the relation? And the relation is essentially the fact that if you sketch the Bode plot of the transfer function, right? So what will be V naught over Vi? What will be the transfer function in this particular case? It will be omega naught C2 or C2 times RL by under root 1 plus omega naught square RD plus RL whole square. Right? Sorry, yeah, times GM. So if I sketch the Bode plot of this, what should I get? I should get something going up, and at infinite frequencies, it will be flat. Right? So omega naught term goes off, right? At omega tends to infinity, omega naught term cancels off. And what is this corner frequency? I missed a C2 here, right? This corner frequency is 1 over C2 times RD plus RL, which is essentially the time constant. Right? So your time constant gets related to the corner frequencies of Bode plots for first order systems. Okay. And this should not also surprise us, because ultimately, when we say that your capacity, when you are giving a sinusoidal input and you are hoping that the capacitor acts as a short, we are essentially saying that the capacitor has to be large enough. Right? Large enough with respect to something. Now, a capacitor becoming large enough in terms of time constant parlance means that the time constant has to be large enough. Right? So those two things become related simply because we are essentially arguing about the same thing from two different input standpoint. Right? So it should not surprise us that they are related. And the part that is, I would say, serendipitous is the fact that your time constant actually matches that corner frequency. I mean, one might argue that it could have been some alpha times beta times, but it actually matches. I would argue that is probably a matter of dumb luck. Or just that the math turns out like that. Okay, but it should not surprise us that they are related. Okay, this is critical because as we proceed, we will be using these concepts of corner frequency, time constant very interchangeably. Okay, so we'll just say that find out the time constant. If I know the time constant, I'll try to figure out what is the corner frequency of a Bode plot, and so on and so forth. Okay, fine. So now let's move on. So before we stopped in the last class, I made a comment that ultimately I would want all the incremental current. This is VI. This is incrementally VI again. Let me sketch this full stuff. So the incremental current through this transistor, is GM times VG. This incremental current through this transistor gets getting divided when it's appearing at this node, right? So I had made one comment that I don't want to divide. I want all the incremental current to flow into my load, which naturally means that I need to increase the value of RD, right? Or if I have to make a perfect argument, I should say RD should be much, much greater than RL, assuming C2 is short, right? RD has to be much, much greater than RL if all the current has to flow into RL, right? So, but what is the problem? The problem is this is all good in the incremental picture, but I also have a biasing picture to satisfy, right? So if I increase RD, if I keep on increasing RD, what will happen is I'll not be able to, where did I go? Yeah. So I'll not be able to ensure that the transistor remains in saturation for a fixed supply voltage. I keep on increasing RD, which means the drop across RD will keep on increasing. Assuming it's if the transistor is in saturation condition, then the current drawn through the RD will be constant. And if I keep on increasing RD, the voltage across RD will decrease, which means there is only certain amount of RD, certain value of RD, maximum value of RD that I can achieve under a given voltage VDD, and assuming that transistor is in saturation. So, which means that I have run into a problem that this condition of RL to be much greater than RD will only give me so much of gain. Now, then I argued that, wait, what if I could have replaced this RD with a current source? Right? So in the total picture, if I could have replaced this RD with a current source, some current source ID, right? Let's say I was able to do that. Then it makes sense that in the incremental sense, what is happening in the incremental sense, all the current can now flow into RL, right? And that is easy to see from this total picture also, that what is the quiescent current through this? If everything is biased properly, the quiescent current through this will be ID, right? That's how I have fixed the value of ID. If the quiescent current going into the node has to be equal to the quiescent current coming out of the node. Yes.
How do you know that there will be some current division for T2?
Okay. Will there be a current division in under quiescent condition? No, because the capacitor is open. It's a DC. No current can go in. No current can go in here, right? So there will not be any current division. And if I do my maths correctly, and I set the value of ID exactly equal to whatever it's supposed to be, then all the current will flow into the all the current will flow into the all the current that flows into the transistor will be exactly equal to the current, exactly equal to the condition of saturation. Okay. So now on top of that, if I apply an incremental voltage, right, which is VI, the current that the incremental current that the transistor will spit out will be this plus GM times VI. Now the current that is flowing in is ID, current that is flowing out is ID plus GM times VI. There is a difference in current. And where will the difference current come from? It comes with only one path to come from. It can come through this, and this will be GM times VI. And naturally, the voltage here will be minus GM times VI times RL. Okay, why don't you tell me what was the use of the RD before? If I didn't have an RD, I mean, let's assume that we didn't know how the capacitor was, your current source was a solution. Yes, somebody made a comment here.
Output voltage.
Exactly, right? So if the RD was not there, and let's assume the RD was shorted to VDD, right? I mean, if this was shorted to VDD, then all the incremental current would have flown into that VDD. It's an incremental round, no change, right? So the output would have been steady at 0, right? So it wouldn't have served our purpose. So, but however, if I can do this,
Then normally if we are using RD, we need it to be a very high current.
exactly,
But then we also can't.
which is the problem, exactly, right? So this is good, right? This can solve our issue, but there is one important problem. As it turns out, if you hook up this circuit in the lab, it probably will work for one very sweet spot, but it will not work beyond that. And the reason is as follows. Okay, before I go into the reason even, let me go back to a very basic, an extremely fundamental question. So when I say that the total current ID is of mu n Cox W over L VGS minus threshold voltage whole square. What am I essentially saying? What is the dependent variable and what is the independent variable? Exactly, right? So this is VGS is the independent variable and ID is the dependent variable. In terms of design parlance, what we'll say that VGS is the cause and ID is the effect. Right? Note that it doesn't come out mathematically. If you just give somebody this equation, it's not particularly evident, right? I can interchange the variables from left and right and do all those things, but it's not particularly evident, right? That one is the cause, other is the effect. But it's the way the device functions that ensures that that will determine which is the cause, which is the effect, right? And why am I saying this? Looking into this equation, you might think, you shouldn't think, but one might think that if I stick in a current ID, magically a voltage VGS will appear at the input. What I'm trying to get at here is that if you only stare at this equation is telling you certain relationship between ID and VGS. Correct? So if I make an argument that I'll take a current source, put it into the drain, as I have shown here, will this transistor be in saturation? Right? No, this is exact. This is what you have. So, okay. So let's assume you have gone to the lab and you have used this setup. Okay. No, nothing else. No, nothing connected to drain, nothing connected to source. Whatever you have is, source is grounded, but nothing else. So can you guarantee that this stuff will be in saturation? It's an ideal current source, so ID has to flow. If it's an ideal, yes, but I understand what you are saying. I'll come back to that. But let's assume that this is what you have done. Something will go wrong, right? Why? Because in this case, you are hoping that if the transistor is biased properly, then some voltage has to appear across its gate to source terminals, because that is the cause. Right? So looking into this equation will not give you that picture, but the property of the device, it has to be, the way the device works is VGS is the cause and ID is the effect. If you have not applied the cause, you shouldn't expect an effect. Right? So you don't know what is going to be. VGS can be anything, right? So it's not defined. Now, he made a comment that ID will shut off or something, right? Yeah. So it might or it might not. It depends upon certain conditions. I'll come back to it. Okay. So now let's assume that I told you that you go to the lab and I gave you a current source, right? I gave you a current source and I told you you have a bunch of variable voltage sources available to you. You have a current source, you have this MOSFET. Ensure that I drive the drain of the capacitor of the MOSFET with the current source, just like the way it has been shown here. But you have to ensure that this stuff is in saturation. What will you do? You have all sorts of equipments available in the lab. You have variable voltage sources, current sources, everything available. But I want to ensure that this transistor is in saturation. You will find the value of VG means what? Okay, good. One step you are closer, but help me through here. When you say you are going to set the value of VGS, what do you mean? You are in the lab doing an experiment. Not a voltmeter, voltage source, right? Okay, some more ideas. Why? Yes, but we'll come to that. But let's assume that you don't know that is the solution. How do you come to that solution? That's essentially the question. Yeah. So that's what, right? If I give you a circuit, it's very easy to analyze. But the whole of this course is to develop the thought process as to how do you come up with it. So again, think that you don't know what the device is. It can be anything. If I tell you that you don't even know that the value of mu C ox W by L, it's a black box to you, right? So I can tell you what I will do. In fact, all of you will do the same thing if I throw you in the lab. So what you will do, you will first just connect ID and MOSFET like this, and you know that you need to have certain voltage here. So you will probably take a variable voltage source and stick it in here. And you will just hope that the current sinks properly. right? Anybody will do that. In the absence of information, this is the minimum thing that I can do. I can start off, right? So, and if you just pick some random values, it need not necessarily be that you have found out the optimum VGS, which should be equal to ID, because you're just stuck in a variable voltages. So let's assume that let's assume that your VGSQ is such that it is lower than what is expected, or rather, you started off with a very high value of VGSQ. Okay, you just stuck in a very high value of VGSQ. How will you observe? What will you observe to figure out whether the transistor is biased in saturation or not? Note that you can observe voltages. You can observe the terminal voltages, right? So this is your black box. You can obviously observe this because you are applying it. You can observe this, and source is grounded. Doesn't matter if you observe it or not. Yeah, so essentially what you will observe the voltage at this node. You know the voltage that you have applied, right? So this is V applied, let's say. You will observe VD, and you will conclude something. If VA, or rather, if you observe that VD is going, let's say VD is greater than VA minus, or rather, you applied a very large value of VA, right? So if you observe that VD is less than VA minus threshold voltage, what will you conclude? The transistor is implies linear region or triode region of operation, right? And both are same. Okay, so, and let's assume that you have found that this is the condition that, you started off with this and you found this is what it is. So what will you do?
Increase the voltage.
Source is grounded for the time being. You have to decrease VA. You will decrease VA and you will observe VD, right? And you will keep on doing it till you see the difference between VA and VD are within one threshold voltage, right? Then you know the transistor is in saturation. So what is the thought process that is playing out? The thought process that is playing out at the back of our mind is this: if VD is less than expected, right? Decrease VA, and other way around, I can say if VD is greater than expected, then increase VA. Yes.
What effect would VA would have? So it's already saturated.
Okay. So let me ask you this question then. Let me ask you this question. So let's take this example. Let's take some numbers, right? So let's assume mu Cox W over L is 2 milliamp per volt squared. Okay. And this is supposed to be 1 milliamp.
Basically, the entire problem that we're dealing with right now is that the current source has to exactly be
Exactly.
which is hard to determine.
Exactly. That's what it is, right?
What have we done till now?
We haven't done anything to fix it. We will do. So coming to his question, that let's assume this is what it is, and you applied a voltage of let's say threshold voltage is 1 volt. I applied 3 volt. What do you think will happen here? Will this be in linear region or in saturation region? It is easy to see if I sketch the ID-VDS plot. ID-VDS. The expected plot is, if I am, let's assume that I am operating here. If we assume that we are operating here, then regardless of the value of VDS, I have 1 milliamp of current. But in order to figure out what, this particular plot is specific to one particular value of VGS. VGS is a parameter. in the way that I have sketched, this particular plot will be possible only when VGS is equal to 2 volt, right? Because only when VGS equal to 2 volt, this mu C of W by 2L times VGS minus VT whole square will go to 1 milliamps. No, this plot is valid only when VGS equal to 2 volt, right? Because forget about this. So 1 milliamp is equal to half mu n C of W over L VGS minus VT whole square. If you set VT is 1, if you set VGS equal to 2 volt, you get that, right? But what happens if VGS is slightly higher than 2 volts? Right. So when VGS is slightly higher than 2 volt, I am hoping that I will have larger current. Right. But my transistor, the current source on top cannot provide larger current. Correct? So what is the only possible solution? Maybe I was expecting to be here, but I mean the current source. I'm sorry. I mean, if I apply a VGS equal to 3 volt, if I apply now a VGS equal to 3 volt, for example, I'm expecting my current curve will be something like this. Correct? And maybe I was expecting 4 milliamp current, but I am now limited by my current source, which is giving me 1 milliamp of current. So I was expecting to be here, but I have to come down to 1 milliamp, which means I have to go all the way from here to here. So I will end up being in linear region, right? So what is the fix to that? The fix to that is to observe the fact that I can figure out whether I am in the right operating region by looking at the relative difference between drain and gate. Okay, and the argument that I laid out was, if I simply see how the drain is moving, if I increase the gate, then that is a good enough measure for me to figure out whether I am going in the right direction. Okay, so if I increasing drain, if I am increasing gate, or rather, I think we are over time. Okay, let me stop here. Otherwise, we'll push the next class. We'll stop here. We'll meet tomorrow. Tomorrow we don't have any tutorial. We'll meet. Okay.